Hello, everyone. This will be our last lecture for the entire semester, which is just wild to think about. I got a little mushy in our Friday information page for today, but this is it. We're bringing it to a close, and as I mentioned in that information page for today, I'm just so thankful to have gotten to know all of you this semester and appreciative of all of the patience and resilience that you've all shown throughout such a chaotic time, to say the least. So yeah, that's as mushy as I'll get about it for now, but just know I appreciate all of you very much. So today is very, very brief. This is a very short lecture on the stratospheric ozone layer. So we'll just chat through these and that'll be that. Also, I've got your final exam study guide posted in the Friday folder. So that's there and good to go. If you're exempt from the exam, congrats. Proud of you. If you're not, then I would definitely recommend looking at the study guide. Despite it being very similar to a regular unit test, still you don't want to mess around with this one since it is worth such a large percentage of your grade. All right, so the ozone layer, this is the good layer of ozone. This is the ozone that we like that is in the stratosphere. So the ozone layer absorbs UV radiation, and it absorbs specifically the UV radiation that is capable of between 210 and 290 wavelength. And it's specifically the radiation, the radiation at the wavelengths that can harm biomolecules like DNA. So it absorbs the wavelengths that could hurt us, which is nice. It's a consequence, this layer's existence is a consequence of oxygen-only chemistry. And this is because a significant amount of oxygen appeared on the Earth about 2 billion years ago due to the rise of cyanobacteria. So there was a really, really large amount of cyanobacteria on the Earth about 2 billion years ago, and they released a ton of oxygen. So that is why we have the ozone layer now. So this probably looks familiar to you guys. Closer to the start of the year when we talked about layers of the atmosphere, you guys actually labeled a diagram very similar to this. You can see a lot of different things here. You've got your troposphere, stratosphere, mesosphere, and thermosphere, and then when you go way, way out, the exosphere, altitude on the left, and chemical makeups over here on the right, and then just kind of what exactly is in each layer, what noteworthy things, satellites out here, rocket planes versus regular airliners, things like that. Oh, and obviously our ozone layer is in the stratosphere, which we should hopefully know. It exists roughly 45 to 60 kilometers above the Earth, the stratospheric ozone layer does. And it has the ability, like we said, to absorb ultraviolet radiation or UV radiation and protect life on Earth. The process for how this happens, basically that UV radiation breaks the bonds holding together the oxygen molecule, leaving 2 free oxygen atoms. And then sometimes those free oxygen atoms result in ozone, when regular oxygen, O2, gains another oxygen atom. The ozone is then broken down into O2 and free oxygen atoms when it absorbs both UVC and UVB ultraviolet lights. There are certain chemicals that can break down ozone, particularly chlorine. And in the stratosphere, the major source of chlorine there is known as chlorofluorocarbons, which is very fun to say, but is not a good thing. CFCs are really dangerous to our atmosphere. They're used in refrigeration and air conditioning, and most notably, I suppose, as propellants in aerosol cans and as blowing agents to inject air into foam products like styrofoam. So nowadays, aerosol cans, it's required, I believe, that they be CFC free. So it's still compressed air, but without the chlorine in it as well. So something to note. So you can see just a little bit here of the, I feel like there are supposed to be words here. of the annual global total ozone in both from 1960 to 2100 are estimate. But when CFCs are released into the troposphere, they make their way to the stratosphere. So if you're using an aerosol can on Earth, obviously, that has CFCs in it, then eventually they do make their way all the way up to the stratosphere. And that UV radiation present has enough energy to break the bond connecting chlorine to the CFC molecule, and that then breaks apart the ozone molecules. So that process looks like this. First, chlorine breaks ozone's bonds and pulls off one atom of oxygen, forming a chlorine monoxide molecule and also oxygen, O2. Then that free oxygen atom pulls the oxygen atom from the chlorine monoxide, which frees up the chlorine atom and creates one oxygen molecule. But what gets dangerous is that one chlorine atom can catalyze the breakdown of as many as 100,000 ozone molecules before it leaves the stratosphere. So even one atom of chlorine can really, really, really mess up other oxygen molecules that form the ozone layer. So you can kind of see ozone production and ozone destruction here in both of these graphics if you want to pause and take a look at those. Global ozone concentrations had actually decreased by more than 10%. The depletion was at its highest near the North and South Pole. And that decreased stratospheric ozone increased, obviously, the amount of UVB radiation that reaches the surface of the Earth. So because we had less ozone, we had more UV rays that were able to reach the Earth. So you can kind of see the extent of the ozone hole. We've got 1979, 88, 98, and 2008. And you can see exactly where it got broken down the most. It was already thin up here, thinner, until there's almost nothing left at all in 2008. And then down here, the isolated concentric region around the Antarctic continent is called the polar vortex. So this polar vortex up here is where most of the damage was. So as of 2012, this is what we're looking like. Which actually, if you look between right here, the 2008 model, look at this left side, and then look at it now. So really, there have been some improvements. It is more narrow. It's still bad, obviously, but some progress from 2008 to 2012, which is a very good thing, and in large part due to those CFCs being outlawed. So you can see the false color view of the monthly average total ozone over the Antarctic pole. And ideally, this is 2019, so even more updated. And now we're looking pretty darn good, especially when you look 2012. And now it is getting much better. It could continue to heal and completely close up by 2050, which would be ideal, obviously. So that is what we've got for today. Make sure you look at your study guide. And as always, if you have any questions at all, reach out and let me know.